Two identical balls of mass m are hung from non-conducting threads of length L, as shown in the sketch on the right. They each carry an identical charge Q. Assume that the angle theta is so teensy-weensy that the approximation you learned in trig that tangent theta is approximately sine theta for small thetas is true. Using this approximation, show that x equals q squared over L divided by 2 pi epsilon naught times mg all to the 1/3 power, where x is the separation between the balls. Okay, so the trick to doing this problem is making a force diagram. So first we're given quantities L, x, and q. Each is referring to the charge, this referring to the distance between the two balls, this referring to the length of the string. And we have this some angle theta. So if we draw a force diagram, say on this ball here, we have the weight that's going down, we have the tension, so this is tension times cosine theta, so like cosine theta right there is acting up in the y direction. Then we have the force of electricity between the two, or rather the electrostatic force between the two balls, and that's going away from each other because they have the same charge. And then we have the tension times sine theta, which is pulling towards the ball. So now that we have that, we can calculate our electrostatic force, and that's 1 over 4 pi epsilon naught times q1 times q2 divided by r squared. And then here we can just simplify as q squared since it's the same charge, divided by 4 pi epsilon naught, and r is now x, so x squared. So if we sum up the forces in the y direction, we get tension cosine theta minus mg is equal to 0. They're in equilibrium, they're not moving. The point of doing this is to isolate tension, because later that'll come in handy. So if we isolate tension, we get tension equals mg over cosine theta. Now if we sum up the forces in the x direction, things are going to get a lot smoother. We have the electrostatic force minus the tension is sine theta times sine theta. That's also in equilibrium. And then we can substitute right here for tension as mg over cosine theta. We get force Fe minus mg tangent theta, because sine theta over cosine theta is equal to tangent theta. That's equal to 0. And then we use this small angle approximation that they told us in the question to give us mg sine theta. We just convert it right back. Sine theta, tangent theta, sine theta. So from that, then we can use another thing that we have to do. And here's what it is. So remember that triangle we drew? Okay, now instead of doing it in terms of tension, we're going to do it in terms of distance. We have length, we have x over 2, and we can confirm it over here. Imagine this goes down to here at the midpoint of x. And then we have length, and then we have just that those quantities, and that's all we're going to need. So from that, we can say sine theta is equal to x over 2 divided by L, right? So sine theta x over 2 over L. That's the same thing as x over 2L. And we can, once we add mgx over 2L to the other side, so we substitute sine theta there. So we substitute sine theta there, which is x over 2L. You see that change. And then once we add to the other side, we can substitute force of the electrostatic force for what we calculated up here. Now it's just algebra. We just isolate x, and then we should get q squared times L divided by 2 pi epsilon naught times mg all to the 1/3 power.